those halogen-forming reactions are sort of unique in that we have the alcohol become a leaving group and then it has its own nucleophile that comes in and attacks it. We can separate those steps out by using a tosylate. So we can just make an alcohol into a good leaving group with this reaction right here. So I have an alcohol, I have paratoluene, right? Sulfonyl chloride. Here's a sulfonyl, S2 double bond O's, Cl, right? Para methyl group, right, across the benzene ring. So that's paratoluene sulfonyl chloride, known for short as tosyl, T-O-S-Y-L chloride, or TOSCl. What happens, pretty simple reaction. I'll draw the first step for you. Okay. O attacks the sulfur, kicks electrons up on one of those oxygens. In the second step, they'll come back down and they'll kick the chlorine off. So 2 steps, but what we end up with is RO attached directly to the S, okay, of that sulfonyl group. So this is our tosylate that we've formed. We could call it ROTOS. Right, so I've essentially replaced the hydrogen of the alcohol with the tosyl group. This OTOS part now is a good leaving group. So it's essentially a tosylate, right? An O with the TOS on it is essentially just like a halide or something like that. That's an excellent leaving group. The carbon is electrophilic, attached to it. The whole OTOS group will be kicked out then. So let's look at stereochemistry here. Stereochemistry of the alcohol is retained when forming a tosylate since the CO bond is untouched. Very important. If I have an R alcohol, that makes an R tosylate. So OTOS. It's essentially just replacing the H of an alcohol with that tosyl. Right. TOSCl with pyridine. Pyridine is just it's like benzene with a nitrogen in it. So weak base that's used to facilitate the removal of the proton there. So tosyl chloride and pyridine is the, so I write TOSCl and then PY under the arrow, and that's understood that we're making an alcohol into a tosylate. Any nucleophile can then attack that tosylate by an SN2 reaction, and that will invert configuration. So let's take a very close look at this reaction sequence. Let's start with this R alcohol. If I react it like we did on the last page with PBr3, that makes an S bromo compound. So there was one inversion. If I attack that then with a nucleophile like an alkoxide, we end up with another inversion. So here I've got an R ether. Okay. We could add any nucleophile to this, right? Anything that's a minus, really, and that'll displace the bromide. So what the deal is here, we got a nucleophile directly in the same position that that alcohol originally was in. Okay? Compare that with taking an alcohol, making a tosylate out of it, where there's no inversion. This is retention. Right? Because again, the CO bond is untouched. We just replaced the H with the tosylate. Now, a strong nucleophile can attack the tosylate. And now I end up, and that was an inversion, I end up with an S ether, right, where the nucleophile is in the opposite position that the OH group was in. So double inversion ends up as retention, right? If I go from an R to an S, I can go back to an R. If I form a tosylate, it remains an R, and then I have a nucleophile, which I can attack. So down here, it's only one SN2 reaction, right? Only one time when we attack from behind where the leaving group is kicked out. The formation of the tosylate is not an SN2 reaction. It's just an acid-base reaction, essentially. Up here, where I formed the bromide, that's an SN2 reaction. We have a PBr2 leaving group which adds, and then the bromide comes from behind. Then I can take another nucleophile and displace that bromide, and that's a double inversion. So single inversion versus double inversion can give us either stereoisomer. Let's just practice on this compound. We have a cyclohexane, hydroxyl going back, methyl coming forward, just next to each other, just so we have a point of reference. If I want to replace that hydroxide with some sort of nucleophile, let's say cyanide, Cn- is a great nucleophile, I have access to either retention or inversion of configuration there. Okay? I can retain configuration by first using PBr3 and then adding cyanide. Right? Each of those is an inversion, so we'll have double inversion. I'll have cyanide added the same direction as that hydroxyl originally. Now, if I want to invert, if I want to have cyanide going the opposite way, what I have to do is make it a tosylate. So, step 1, tosyl chloride with pyridine, Py. Step 2, addition of cyanide. Since I only have one SN2 reaction here, I will have inverted the stereochemistry there. Okay? So be familiar with that sequence. Notice the key difference here. Stereochemistry of that right there. Okay? Single inversion with the tosylate, and then nucleophilic attack, double inversion with PBr3 and then nucleophile.